Hello everyone. Have you ever wondered why some wires get hot when you switch on a fan or a bulb? Well, it's all about resistance, the tiny invisible force that says, not so fast, to electric current. Here's a little physics joke for you. Why did the electron break up with the proton? Because it found resistance too electric to handle. Alright, now let's understand what resistance really means. Resistance, symbolized by the letter R, is a measure of how much a conductor opposes or resists the flow of electric current through it. Imagine a pipe with water. Resistance is like a narrow spot that slows down the water flow, and just like rubbing your hands together produces heat, this resistance causes the conductor to produce heat when current flows. This resistance depends on two main things: the material the wire is made of and its physical dimensions, such as how long and thick it is. This fits perfectly with Ohm's law, which tells us that resistance R equals the potential difference we divided by the current I. In words, resistance is equal to voltage divided by current. And how do we measure this resistance? In ohms, denoted by the Greek letter omega. 1 ohm is simply 1 volt per ampere, meaning if 1 volt pushes 1 ampere of current, the resistance is 1 ohm. So next time your phone charger or a wire gets warm, remember that resistance is at work, quietly putting the brakes on those zipping electrons. Hey physics explorers! Ever wondered why a thin wire in your phone charger gets hot faster than a thick one? Well, it all comes down to how the shape and size of a wire influence its resistance, the wire's opposition to the flow of current. Let's start simple. Resistance increases with length. That means if you double the length of a wire, the electrons have to travel twice as far, bumping into more atoms along the way, just like a longer hallway means more steps before you reach the end. So mathematically, R is directly proportional to L. Now, resistance also depends on how thick the wire is, or in physics terms, its cross-sectional area. The thicker the wire, the easier it is for electrons to pass through. So, R is inversely proportional to A, meaning if you double the area, the resistance becomes half. A thin wire, high resistance. A thick wire, low resistance. When we combine both ideas, we get R is proportional to L divided by A. This means doubling the length doubles resistance, but halving the area doubles it too. And guess what? Experiments agree. That's why long, thin wires have higher resistance, while short, thick ones are better conductors. So next time your charger warms up, remember, it's not just working hard, it's also showing off a physics law in action. Hey there, science enthusiasts! Have you ever wondered why wires are made of copper and not, say, rubber? That's because different materials resist the flow of electricity differently, and that special behavior is captured by a property called resistivity, denoted by the Greek letter ρ. Now here's how it works. The resistance of a wire doesn't depend only on its length and thickness, but also on what it's made of. And that's where resistivity steps in. The relationship is given by the equation R equals ρ times L by A, where R is resistance, L is the length, A is the cross-sectional area, and ρ is the resistivity, a constant for each material. So, what does this tell us? If ρ is low, like in copper or silver, the material is a good conductor, electricity zooms through it with ease. If ρ is high, like in rubber or glass, it's an insulator, current struggles to pass through. And here's a neat fact, resistivity is measured in ohmmeter and, unlike resistance, it doesn't depend on the size or shape of the material, only on its nature. So, the next time you plug in a copper wire, remember, it's not just metal, it's a carefully chosen hero with just the right resistivity to keep your circuits running smoothly. Hey curious minds! Have you ever noticed how your phone warms up after long use, or how electric wires get slightly hot when too much current flows through? That's not just heat, it's thermal agitation in action. Here's what's happening behind the scenes. As temperature increases, the atoms in a conductor start vibrating more rapidly. These vibrations act like tiny roadblocks for moving electrons, making it harder for them to flow smoothly. The result? Resistance increases with temperature. For most metals, this relationship is quite neat and predictable. It's given by the formula R sub T equals R naught multiplied by open bracket 1 plus alpha multiplied by open bracket T minus T naught close bracket, where R naught is the resistance at the reference temperature T naught, T is the new temperature, and alpha is called the temperature coefficient of resistance. It tells us how strongly the resistance changes per degree rise in temperature. In simple terms, higher temperature, higher resistance for metals. But here's an interesting twist. Some materials, especially semiconductors, behave the opposite way. As their temperature increases, their resistance actually decreases. This phenomenon is known as the negative temperature coefficient. So, while metals become more resistive when heated, semiconductors get more conductive, and that's one reason your electronic devices rely on them. Pretty cool, right? Alright, science explorers, let's dive into the world of resistivity. Every material has its own unique resistance to electric flow, and that property is called resistivity. Let's start with the superstars of conduction, metals. They have very low resistivity, which means they allow electric current to flow easily. For example, silver has a resistivity of 1.6 times 10 to the power minus 8 ohmmeter, and copper is right behind at 1.62 times 10 to the power minus 8 ohmmeter. That's why metals like copper and silver are our top choices for wires. They barely resist electricity. Now, let's jump to the opposite side, insulators. Materials like glass have resistivity ranging from 10 to the power 10 to 10 to the power 14 ohmmeter. And rubber? Even higher, above 10 to the power 13 ohmmeter. That's huge compared to metals. No surprise they're used to coat wires and prevent current from escaping. So here's the big idea. Low resistivity, perfect for conductors that carry current. High resistivity, ideal for insulators that protect and block current. All these values come from careful experimental measurements recorded in tables for us to use. So the next time you see a copper wire wrapped in rubber insulation, remember, it's not just everyday material, it's smart science choosing the right tool for the right job. Alright, young scientists, let's put our knowledge into action. Today, we are using the resistance formula. Resistance equals resistivity multiplied by length divided by cross-sectional area. Now, here's our data. We have a copper wire that is 2 meters long. Its cross-sectional area is 1 square millimeter, which we convert to 1 times 10 to the power minus 6 square meters. And copper has a resistivity of 1.7 times 10 to the power minus 8 ohmmeter. Our goal, find the resistance R. Now let's plug in the values. R equals 1.7 times 10 to the power minus 8 multiplied by 2 divided by 1 times 10 to the power minus 6. Let's calculate the numerator. 1.7 times 2 equals 3.4. So we have R equals 3.4 times 10 to the power minus 8 divided by 10 to the power minus 6 dividing powers of 10. Minus 8 minus 6 equals minus 2. So, R equals 3.4 times 10 to the power minus 2 ohm. And writing that as a normal decimal, R equals 0.034 ohm. That's a very small resistance value. Why so small? Because copper is an excellent conductor, it offers very little opposition to electric current. And here's a quick logic check. If we used a thinner wire, meaning a smaller cross-sectional area, the resistance would increase because electrons would have a narrower path to flow through. So yes, everything makes perfect sense. This example shows how material property, the resistivity, and geometry, the length and area, work together inside the formula. R equals rho times L divided by A to decide how easily current can move through a wire. Science and math teaming up perfectly. Alright, learners, let's wrap it up and recap everything we've explored about resistance and resistivity. We started with the key formula R equals rho times L by A, where resistance depends on the material's resistivity, its length, and its cross-sectional area. Now, remember, resistivity is a material-specific property. It's what makes copper a great conductor and rubber a great insulator. We learned that resistance increases when the wire is longer, but decreases when the wire is thicker, so geometry plays a big role. Temperature also joins the party. For most metals, heating increases resistance because atoms vibrate more, blocking electron flow. But in materials like semiconductors, it's the opposite. Resistance actually goes down. And finally, proper material selection matters. Using materials with low resistivity, like copper or silver, ensures efficient current flow and minimizes energy loss in circuits. So next time you plug in a device, think of it this way: a perfect balance of physics, material science, and smart engineering is keeping that current flowing safely and efficiently.